Hey everyone, this is a brushed DC gear motor driven by an L298N and an Arduino Nano ESP32. The motor spins at 300 RPM. I apply friction on the wheel. Watch the PWM trace. The controller reacts in milliseconds. The speed barely moves. In most hobby projects, the default is to tune by feel. If instead you first identify the plant, the system being controlled, here the motor, you can derive the gains in 3 lines of algebra. The pipeline, measure the plant, fit a model, design analytically, discretize, flash. We work in the Laplace domain, where systems become transfer functions and differential equations become algebra. For our motor, we have the equation P of s equals k over tau s plus 1. 2 parameters, k, the DC gain, and tau, the time constant. To measure them, we apply a step PWM and record the velocity. The step response of a first-order system is an exponential rise, the same curve a capacitor follows charging toward a supply voltage. V of t equals k times 1 minus e to the power of minus t over tau. A least squares fit to the data gives us k equals 2.787 RPM per unit PWM and tau equals 0.112 seconds. We use a PI controller, no D term, because the plant doesn't oscillate and differentiating the noisy encoder signal would only add jitter. In series with the motor, the open loop transfer function is controller times plant, CPI of s times P of s. The PI controller has a 0 at s equals minus ki over kp. We place it on the motor's pole at s equals minus 1 over tau. They cancel and the open loop collapses to a pure integrator. The closed loop then becomes T of s equals 1 over tau closed loop s plus 1. Tau closed loop is our free design knob. We choose tau closed loop equals 50 milliseconds, which then gives kp approximately 0.804 and ki approximately 7.17. Taking the inverse Laplace transform and discretizing for a 5 millisecond loop, the controller becomes this in C++. The one thing the textbook omits, anti-windup. When the output is saturated, the integrator keeps accumulating, and when saturation lifts, the pent-up integral causes overshoot. One if statement fixes it. That is the only meaningful difference between textbook PI and firmware PI. To validate our controller, we perform 2 experiments. A step response to check the design, and a disturbance rejection to show why the integral term matters. To assess the step response, the motor starts from rest. The set point then jumps to 300 RPM. From the data, a least squares fit gives a closed loop time constant of around 42 milliseconds, close to the 50 milliseconds we designed for. The response is clean, exponential rise, no overshoot. To look at the disturbance rejection of our PI controller, we have the motor running at 300 RPM. You can see how I apply friction to the wheel. Watch the PWM trace. The controller responds immediately, driving more current into the motor before the speed has visibly dropped. The RPM recovers to 300 within about 150 milliseconds. Same motor, same load. With a proportional only controller, the RPM drops and settles at the lower speed and stays there. This is steady state error. A P-only controller can only push harder if the error is larger. Under constant load, it reaches an equilibrium with a permanent offset. No matter how long you wait, the error never goes away. We could reduce that offset by increasing Kp, but we can never eliminate it entirely with proportional control alone, regardless of how high we set the gain. The difference between these two responses is the integral term. One extra state variable, one extra line of code. That's it. The motor doesn't know whether you guessed the gains or derived them. But we do, and that's the point. Let me know if you have any questions or suggestions, and see you next time.